modeling efforts at NCI, global ocean models in particular, and to start, naturally I'll show a picture of the atmosphere. And this is a picture of the surface pressure and winds, and I'm not going to go into detail what's going on, but the main feature of the atmosphere, if you look at these kind of snapshots, is that you look at disturbances that are on the order of tens of degrees or thousands of kilometers. And you can see that in more detail, see that in more detail in Australia and in the US. I think that's actually a hurricane. But the main picture is that to model the sort of first level turbulent dynamics of the atmosphere, you have to get on the scale of tens of degrees. So the story is very different in the ocean. Those were observations I showed. This is also observations of sea surface height in the Southern Ocean. And to capture the turbulent dynamics of the ocean, you have to be on very, very small scales, on the order of 10 kilometers, or really about a tenth of a degree of latitude. And so that puts much more computational pressure to get these things running if what you care about is the dynamics. It doesn't mean you need a 10th degree model to capture what's going on in the ocean, but if you want to include ocean dynamics, you do need a lot of resolution and a lot of grid points. And so how many grid points do you need? Well, this is a picture from a paper a few years back, over, characterizing it. And what it comes down to is that you basically need to get around 10th degree latitude to capture the major length scale of the turbulence of the ocean. And that's particularly true in the Southern Ocean, which is more relevant to Australia maybe than other parts. North America tends to focus on here, and Japan tends to focus here, for example. But just global simulations need very high resolution. So how do we model these things? Well, this was a math meeting, so I thought I'd put some math stuff. But I won't go into it. But basically, dynamically, these models have not actually changed much over 40 years. The Brian Cox model from the 70s, I want to say, maybe earlier. And it's hydrostatic. It's just a momentum balance, Coriolis force, advection of a whole bunch of tracers like temperature and salinity, and then they're volume conserving, so they're Boussinesq. And then there's a equation of state to tie it all together. Dynamically, it's not too hard to write down, but it is a little difficult to solve them if there are so many. And the model that's been kind of the most prevalent at NCI, at least recently, is the modular ocean model out of GFDL, which we have pretty good relationships with and been collaborating with in some ways. It's a pretty fancy model. It supports generalized grids. This is the tripolar grid. It's actually an Australian contribution out of Uni Melbourne, Ross Murray. And it uses pretty advanced finite volume advection. These are very computationally expensive. It also allows for an independent resolution of the free surface. And we also have various parameterization schemes. We don't call them LES in oceanography, but that's basically what they are. And I won't go into all this, but it's a fancy model with a lot of things. How is modeling looking on NCI? The climate modeling has generally focused on 1 degree, which, as I said, doesn't actually resolve that dynamics. But we have kind of been pushing them to move to 1/4 degree, which is getting there. On the forecasting side, say with CSIRO and BOM BlueLink and ocean maps, they are at that resolution, but these are very data forced, and they have also evolved from sort of quasi-high-res to pure high-resolution. And on the research side, say the university sectors, which are interested in the questions of what the dynamics is actually doing, they are actually kind of pushing to these scales. But this is all quite recent in Australia, so really, even only like the last less than a decade, really Australia hasn't really been, is really just catching up in this respect. And the CPU hours, the CPUs required to do that is also going up too, from tens of CPUs to really thousands at the 1/4 degree and tens of thousands at the 10th degree. So how do we achieve that? How do we run these models on lots of cores? Well, we dice them up into little bits and we solve each one like a mini ocean, and then we connect them together through message passing. Because it's basically a hyperbolic system, we're quite lucky in that we basically only need to communicate with our nearest neighbors to evolve this thing. It does require lots of communication, but it's not some big, massive all-to-all thing. It's just local communication. And it enables quite strong scaling and parallelization. I'm just going to kind of quickly look at these two models, the 1/4 degree and 10th degree. I haven't been tracking my time, I'm sorry. So please shout out when I go over. The degrees are rough, the quarter degree is about 1,000 by 1,000 grid points, and the 10th degree is about 3,000 by 3,000, if you like. And we'll see how those run on our system. And this is kind of what we have managed to achieve over the last 2 years, I guess you could say. We have been able, this is an example of the quarter degree model. We managed to get it running reasonably well up to 480, and then we were able to get performance at 960. And then we started to see problems. I won't go into what we did to achieve this, but we were able to make improvements in various ways on system level and code level. And we've been able to get this model to run up to over 15,000 cores, not efficiently, but to get it on there. And we've been able to get efficient performance up to 3,000. I'll just explain this very quickly. This is CPUs here and runtime here. This dashed line would represent perfect scalability, where if we throw twice as many cores, we would get half the runtime. So any deviation from that dashed line represents your efficiency. And so you can see these red X's is kind of the most recent state, and we achieve efficient performance up to about 2,000, and we get reasonable performance at 4,000. And that's highlighted a little more accurately here, but I'll just focus on that. The 10th degree model is kind of a result of that work in the quarter degree, and you can see that in fact it scales wonderfully well. We can get virtually perfect performance up to 20,000 CPUs, which is 40% of Rygen. So this model is essentially as big as we're going to do on Rygen, and it's a pretty good story. And it's really one of the reasons that people have been pushing into 10th degree dynamics. Why do we get those speeds? Well, in fact, if we break it down what we're running is a coupled model between the ocean and a sea ice model, as well as field exchanges with a data-driven atmosphere. And what you can see is that if you can follow these dots, the ocean itself actually scales very well, very efficiently up to 4,000 cores, and you even get speed up at 8,000. It's just the sea ice model and the coupler that has been kind of withholding the performance of this model. And and one of the things we've been able to do is actually pull out the sea ice model and run on independent cores from the ocean. I'll just quickly show the 10th degree model. What you can see is that, as I said, the 10th degree model already scales very well, and really, Rygen's not big enough to reveal the scaling problems of that model, so I'll focus back on the quarter degree. These runtimes show that what we've been able to do is move that sea ice model onto independent CPUs, and as a result, if we go from kind of the highly efficient 960 cores up to about 4,000 cores with the sea ice model independent, we kind of get a modest increase in CPU hour consumption, but a 4-fold or 5-fold increase in runtime. And if we blow out to a really inefficient point, we can even get almost 60 years a day out of this model, which for a quarter degree model is pretty impressive. I don't think this audience may even have context for that, but it's been pretty useful. I guess the way to think about it is to do a CMIP style run, you need to do a few centuries, and those usually are considered week-long or month-long jobs, and this is pretty close to almost a day. A few days to get the CMIP style output. If you want to further break this down, what we can kind of see is that this red line represents the tracer advection, which, as I said, is finite volume. It's very expensive, but it represents a pretty consistent part of the calculation. The trends that are most interesting are in the Barotropic, which is the free surface solver, and some other subroutines like this purple line, which represent the sort of 2D surface calculations. And what you can kind of see is that the problems with scalability actually sort of come down to the free surface solver. And we can break that down. This is the tracer advection. You can see it's very efficient up to about 8,000 cores. This is some vertical physics, which is no problem at all. The problems come in the free surface solver. So when you try to resolve the two-dimensional dynamics and three-dimensional and try to scale them together, eventually the 2D holds you back. And that's even more so with this other operation. So that's something we're looking into, and how to kind of decompose the 2D and 3D calculations. And the last thing I'll just mention is that we've started we used to I used to just focus on scalability, but I've started to kind of look into the efficiency of the calculations themselves. And this is just one first step in that. We started to look at the vectorization rates of these models, and one thing this is the ability of the CPU to do simultaneous operations on every clock cycle. rather than one at a time. And one thing that we see is that the model itself is actually extremely efficient in vectorization. So this model does a really good job in terms of how it computes the calculations. Well, at least this is a good sign that it's doing it. There's further stuff we need to do there. Just as a comparison, these are some other ocean models that we've looked at. This is the next generation of the model, MOM6. Its vectorization rate is quite modest, around 2/3 rather than 90%. And this is another ocean model, NEMO, which is only about 50%. So, I mean, one thing we've been able to conclude is that the MOM5 model is actually really well suited for a machine. And just to quickly wrap it up, this is just saying what I said, is that we need these high resolutions to achieve, just even to resolve the dynamics of the ocean. And the 2D parts of the problem, the 3D parts, while they're computationally expensive, are actually not that big a deal in terms of scalability. And MOM itself is a strong vectorizing code. And so at the moment, we're quite happy with how the MOM5 model is running, and I think it's really enabled a lot of researchers to do new things. And I think I'll stop there.